In exercise 1, let V be the first quadrant in the xy plane. That is, let V is equal xy where x and y both of them greater than or equal to 0. If U and V are in V, is U plus V in V and y. So let us assume two vectors. We have U and V, both of them in V. So if U in V, that's mean U is equal, let us say U1, U2, where both of them U1 greater than or equal to 0, U2 greater than or equal to 0. Similarly, if V is in V, that's mean V is equal V1, V2, where V1 greater than or equal to 0, V2 greater than or equal to 0. Now we need to know if U is in V, V also is in V. Is U plus V in V? So now U plus V will be equal U1 plus V1, U2 plus V2. Now since U1 is greater than or equal to 0, V1 greater than or equal to 0, so both of them is positive. That's mean also U1 plus V1 should be greater than or equal to 0 because the sum of non-negative number is non-negative number. Similarly, if U2 greater than or equal to 0, V2 greater than or equal to 0, so U2 plus V2 is also greater than or equal to 0. From here we conclude that U plus V is in V, since the sum of non-negative number is non-negative. Now for part B, find a specific vector U in V and a specific scalar C such that CU is not in V. This is enough to show that V is not a vector space. So now if we take, for example, let U is in V, where our U is equal, for example, 1 and 2. Both of them is greater than or equal to 0, so they should to be in V. Now we have to find C such that CU is not in V. C is in R, so let's C is equal, for example, minus 1. So now CU will be equal minus 1 multiplied by 1 will be minus 1, minus 1 multiplied by 2 will be minus 2. So from here we see that CU is not in V. Since the first entry is negative, the second entry is negative. We want both of them to be positive. That will give us the vector will be in V. But here we have both of them is negative. So CU is not in V. That means it is not a subspace, or it is not a vector space. So now let us see exercise number 2. So for 2, let W be the union of the first and third quadrant in the xy plane. That is, let W is equal xy where xy greater than or equal to 0. Then either of both of them is negative or both of them is positive. So now if U is in W and C is any scalar, is CU in W? So if U in W, that's mean, so let U is in W. So that's mean, U is equal, for example, U1, U2, such that U1, U2 is greater than or equal to 0. Now for any C in R, we have CU is equal CU1, CU2. The condition for CU to be in W, it should be, if we take the first entry multiplied by the second entry, should be greater than or equal to 0. So now let us check CU1 multiplied by cu2, c multiplied by c squared, u1 multiplied by u2, this is u1, u2. This one is greater than or equal to 0 because it is squared. u1 multiplied by u2, we assume it from the beginning since u is in w, so that's mean u1 multiplied by u2, this one is greater than or equal to 0. So whole thing is greater than or equal to 0, so hence cu is in, so cu in w. Now for part B, find a specific vector u and v in w such that u plus v is not in w. This is enough to show that w is not a vector space. So if we assume let u is equal, we need a vector u inside the w, and we need also vector v inside w. But if we add both of them, this will not give us in w. So if we assume u is equal, for example, let us say it -2, -5. This is in w, since -2 multiplied -5 will be 10. 10 is greater than or equal to 0. And let v is equal, for example, let us say the 3 and 2. This one is also in w, since 2 multiplied by 3 is positive, so this is in w. So now u plus v will be equal -2 plus 3 minus 5 plus 2. This will give us 1 minus 3. If we multiplied 1 by -3, so 1 multiplied by -3, which is equal -3, this one is less than or equal to 0. So from here we conclude that u plus v is not in w, and hence it is not a vector space. You can choose any vector u and v that give you u plus v is not in w, and we conclude from here that it is not a vector space because it is not closed under addition. In 3, let h be the set of points inside and on the unit circle, the xy plane. That is, let h is equal x is xy, such that x squared plus y squared less than or equal to 1. Find a specific example, two vectors or a vector and a scalar to show that h is not a subspace of R2. If we assume that let u, for example, u is in h and u is equal, we want x squared plus y squared less than or equal to 1. So both of them should be less than, let us say this one is 1 over 3, this one is 1 over 3. Where 1 over 3 plus 1 over 3, both of them, if we squared it, the result will be less than or equal to 1, which is 2 over 9. Now we want to find a specific scalar cu. Let's see, for example, it is equal to 3. So now cu is equal 3 multiplied by 1 over 3, 1. 3 multiplied by 1 over 3, which is 1. So now cu is not inside h because 1 square plus 1 square is 2, and 2 is not less than or equal to 1. So this one is not a subspace because it is not closed under scalar multiplication. In 4, construct a geometric figure that illustrates why a line in R2 not through the origin is not closed under vector addition. For example, if we have this line, which is L, if we have the vector u, for example, this one is the vector v, and here we have the vector u, which is this one and this one. So now u plus v is the addition of the vector u plus the vector v, which is this one. So here we will have the vector u plus v. We say that u and v, it is in L, but if we add u plus v, the result will be here, which is not inside L, so it is not closed under vector addition. In exercises 5 to 8, determine if the given set is a subspace of Pn for an appropriate value of n. Justify your answers. So 5. All polynomials of the form bt is equal at square, where a is in R. This here we can write bt as bt is equal span t square. So now if we can write this one as a span, so by theorem we know that every span of vector is a subspace. So from here, since this one can be written as a span, so the set is a subspace. Of Bn. For 8, all polynomials of the form bt is equal a plus t square, where a is in R. This one, it is not a subspace since the zero vector is not in the set. Because here we don't have the zero vector, so it is not in the set, so it is not a subspace. This one is not a subspace. Since the zero vector is not in BT. Sorry, this one is not 8, it is this one also, sorry, this one is 5, this one is 6, now for 7. Now for 7, all polynomials of degree at most 3 with integers as coefficients. So polynomials of degree at most 3 with integers as a coefficients, is this one a subspace? We can say no, because if we multiply the polynomial by a scalar which is not an integer, we get non-integer coefficients. So that means this polynomial is not a subspace because it is not closed under scalar multiplication. يعني إن إحنا عندنا البولينوميال هنا الكوفيشنت مالهم عبارة عن integers. لما أجي أضربها by scalar which is an not integer بيطلع لي polynomial with non-integer. إذن this polynomial, the new polynomial is not in a polynomial with integer coefficients. So that's why it is not closed under scalar multiplication. So no, because it is not closed, under multiplication by scalar. Which is not integers. Now for 8, all polynomials in Bn such that B0 is equal to 0. This one we need to check if it is a subspace or not. First we have the 0 vectors is in H, since we have B0 is equal to 0. So the 0 vector is in Pn. Then we need to check if two polynomials inside Bn is the addition will be inside n. So if B and Q is in Pn, then P plus Q 0, this will give us B0 plus Q0. So this is equal 0 plus 0. So from here we conclude P plus Q is inside Pn. So 3, we need to know if we take any scalar for C in R, and then we need to, what is CB0? This is similarly as C multiplied by B0. So this is C multiplied by 0, which is equal to 0. So from here, CB it is inside Pn. So by 1, 2, and 3, this one is a subspace by theorem 1. So Pn is a subspace. By theorem 1. In 9, let H be the set of all vectors of the form S3H2S, S3S2S. Find a vector V in R3 such that H is equal span V. Why does this show that H is a subspace of R3? So if H is the set of all vectors of this form, that means H is equal, if we take S as a common factor, so this is 1, 3, 2. So if we need to write H as a span of V, so from here H is equal span of the vector, it is all the linear combination of the vector 1, 3, 2. So why does this show that H is a subspace of R3? Because we can represent H as a span of vector. So by theorem 1, it is a subspace of R3. So H is a subspace of R3 by theorem 1. So now for 10, let H be the set of all vectors of the form 2t 0 minus t. Show that H is a subspace of R3. So similarly here we need to rewrite H. So H will be equal, if we take t as a common factor, so this will give us here 2, 0, minus 1. So from here H is equal span all the linear combination of the vector 2, 0, minus 1. So from here, by theorem 1, H is a subspace of R3 by theorem 1 because we can represent it as a span. Now for 11, let W be the set of all vectors of the form 5b plus 2c, b, c, where b and c are arbitrary. Find vectors u and v such that W is equal span uv. Why does this show that W is a subspace of R3? So first we can write W as, since here we have two unknown, which is b and c, so we can take b, then we take the coefficient of b is 5, 1, 0, plus, then the other unknown is c, so the coefficients of c is 2, 0, 1. So from here we can write W is equal span of the two vectors, which is all linear combination of the vectors 5, 1, 0 and 2, 0, 1. So now since we can represent W as a span of two vectors, so by theorem 1, it is a subspace of R3. So you can represent this one as U, this one also as V. So by theorem 1, W is a subspace of R3. Now for 12, let W be the set of all vectors of this form S plus 3t, S minus t, 2s minus t, 4t. Show that W is a subspace of R4. So we need to write this W as, so here we have 12. So here we have two variables also, so S, then the coefficients of S is 1, 1, 2, 0, plus the coefficients of T is 3, minus 1, minus 1, 4. So from here, W is equal span of the two vector, we have 1, 1, 2, 0, and the other vector 3, minus 1, minus 1, 4. So from here we conclude that W is a subspace of R4 by theorem 1, because we can represent it as a span of vectors, so that means it is a subspace directly of R4 since we have 4 elements. So this one is 0. So here it is infinitely many vectors. Now for part C, is W in the subspace spanned by V1, V2, V3? We want to know if W is a subspace spanned by this one. That means is W is a linear combination of these three vectors? Can we rewrite W as linear combination of these vectors? So that means we need to solve V1, V2, V2, V3, and here we have the vector W. If this system is consistent, so that means W is in a subspace spanned by these three vectors. But if it is not consistent, then W it is not. But now if you check this one, since this one has a solution, that means the system consistent, then we can conclude W is in the subspace spanned by the vectors V1, V2, V3. In 14, let V1, V2, V3 be as in exercise 13. And let W is 8, 4, 7. Is W in the subspace spanned by V1, V2, V3, and why? Also, we need to solve this one, V1, V2, V3 with this new W. If the system is consistent, so that means W is in a subspace spanned by this vector. But if this one is not consistent, so that means W is not in the subspace. So now we have 1, 0, minus 1. This is from exercise 13. We have 4, 2, 6. And we have W, which is 8, 4, 7. So now if we do row operation for this one, we will get 1, 0, 0, 2, 1, 0, and 4, 2, 0. And here we have 8, 4, minus 5. So now here, since the system is clear from the last row, it is not consistent. So that means W is not in the subspace spanned by this vector. So from here, no, W is not in the subspace spanned by the vectors V1, V2, V3. In 15 to 18, let W be the set of all vectors of the form shown where A, B, and C represent arbitrary real numbers. In each case, either find a set S of vectors such that spans W, or give an example to show that W is not a vector space. So for 15, it is clear this one is equal if we take A. Then we have a 3, 0, 1, plus if we take B, we have 1, 0, minus 5, then we have 0, 4, 0. So for this one, it is clear does not contain the 0 vector. If we make this one 0, make this one 0, we cannot make this one also to be 0 because here we have it is 4, which is a constant, not equal to 0. So 15 is not a vector space since it does not contain 0 vector. So since the 0 vector is not in W, then W is not a vector space. So now for 16, we can rewrite this one 16. So it is equal to, if we take also similarly A, then here we have minus 1, 1, 1, plus for B, we have 0, minus 6, 2, then also we have 1, 0, 0. So similarly, this one does not contain a 0 vector because we can make this one 0, we can make this one 0, but for this one we cannot make it 0 because here we have 1. So we conclude from here 16 is not a vector space because it is not, because it does not contain a 0 vector. So this one controls. Now for 17, we have A minus B, B minus C, and C minus D. C minus A, and lastly B. If we can rewrite this one as a span of two vectors, so let us write it here. For 17, this one is equal A. The coefficients of A is 1, 0, minus 1, 0, plus the coefficients of B are minus 1, 1, 0, 1. So this is plus C, where the coefficients of C are 0, minus 1, 1, 0. So now this set we can rewrite it as H is equal, or W is equal span of the vectors. If we say this one is V1, this one V2, this one V3, so V1, V2, V3. So since we can represent it as a span, so this one is a subspace or it is a vector space. For 18, we do it similarly like 17, and we get here, let's say here 18. So if we say also W is equal, we have A, then so 4, 0, 1, minus 2, plus B, where the coefficients of B are 3, 0, 1, 0, plus C, where the coefficients of C are 0, 0, 1, 1. So W is equal to span. We say also this one V1, V2, V3. So span V1, V2, V3 And similarly, it is a vector space of R3 or it is a subspace of R3. In exercises 23 and 24, mark each statement true or false, justify each answer. So if f is a function in the vector space V of all real valued function on R, and if ft is equal to 0 for some t, then f is the zero vector in V. This one cannot be true. It is true that it is ft is equal to 0 for some t, but for the zero vector in V, the function f whose value of ft are 0 for all should be for all t in R, not for some t. So this one, A is false. We need all t, not some t. For B, a vector is an arrow in the three-dimensional space. Here we cannot say that any vector or not every arrow is a vector. So for this one is false. B is false. Not every arrow is a vector. So C, a subspace H of a vector space V is a subspace of V if the zero vector is in H. This one is not true because we also need all the other two properties. To be a subspace, it should be closed under multiplication, scalar multiplication, closed under also addition. So it is not enough. So C is false. We need also it is closed under addition, closed under scalar multiplication. For D, the subspace is also a vector space, so this one it is true. No, for E, this one it is not included for you, so just until D. In 24, a vector is any element of a vector space. This one it is true from the definition. Then B, if U is a vector in a vector space V, then -1 multiplied by U is the same as the negative of U. This one is true because U, the negative of U is -U, and if we have -1 multiplied by U, this will give us -U, so this is a true. A vector space is also a subspace. This one is true. R2 is a subspace of R3. This one is false. Because R2 have only 2 elements, whereas R3 it should has 3 elements. So not this one is false. R2 is not a subspace of R3. E, a subspace H of a vector space V is a subspace of V if the following conditions are satisfied. The zero vector of V is in H, U, V, and U plus V are in H, C is a scalar and Cu is in H. For this one, we said this one, the zero vector of V is in H, okay. But for U, V, and U plus V are in H, it said if U in H and V in H, then U plus V should be in H. Similarly, if U in H, then Cu should be in H. So this one cannot be represented like this one. So this one is false. You have to represent it or rewrite it as if U and V in H, then U plus V should be in H. Similarly, if U in H, then Cu should be in H. In exercises 25 to 29, show how the axioms for a vector space V can be used to prove the elementary properties described after the definition of vector space. Fill in the blanks with the appropriate axiom numbers because of axiom 2, axiom 4, and axiom 5 imply, respectively, that 0 plus U is equal U, minus U plus U is equal 0 for all U. So for 25, complete the following proof that the zero vector is unique. So suppose that W in V has the property that U plus W is equal W plus U, which is equal to U. For all U in V, in particular, 0 plus W is equal to 0, but 0 plus W is equal W. By axiom, hence, W is equal 0 plus W is equal to 0. So the axiom here, we can use axiom 4. The 0 is a vector 0 in W such that U plus 0 is equal to U, which is for this one. 0 plus W is equal to W. Also, we use axiom 2. U plus V is equal V plus U. Because here we have U plus W, it is equal W plus U, which is equal to U. So this one is by axiom 2 and 4. For 26, complete the following proof that minus U is the unique vector in V, such that U plus minus U is equal to 0. So suppose that W satisfies U plus W is equal to 0. Adding minus U to both sides, we have minus U plus W is equal minus U plus 0. So we add minus W for both sides. Now if we take minus U with this U, so minus U plus W, this equal minus U plus 0. So we can use this property by using axiom 3, which is U plus V plus W, it is equal U plus V plus W. So this one is by axiom 3. Then here we have it is equal to 0 plus W, and this one minus U plus 0. So minus U plus U is equal to 0. That's mean we use the axiom 5. That is U plus minus U is equal to 0. So this is by axiom 5. So 0 plus W is equal W, minus U plus 0 is equal minus U. So this one is by using axiom number 4. There is a 0 vector 0 in V such that U plus 0 is equal U. So this one is 4. So then for 27, fill in the missing axiom numbers in the following proof that 0 multiplied by U is equal to 0 for every U in V. So 0 multiplied by U is equal 0 plus 0 all multiplied by U, which is equal 0 multiplied by U plus 0 multiplied by this U. So this is just the axiom number 8. If we have C plus D, 2 constant multiplied by U, the result will be Cu plus Du. Similarly, if we have 2 constant, both of them 0 multiplied by U, this will give us 0 multiplied by U plus 0 multiplied by U. So this is by axiom number 8. So add the negative of 0 multiplied by U to both sides. We have 0 multiplied by U plus minus 0 multiplied by U is equal 0 multiplied by U plus 0 multiplied by U, and we add minus 0 multiplied by U. So we take this one, we add minus 0 multiplied by U both sides. So for the first one, for the first left side, we have 0 multiplied by U plus minus 0 multiplied by U. For this one, we can take this 0 multiplied by U with this one, with a negative 0 multiplied by U. So this is using the axiom number, which is number 3. If we have 3 vectors, we can add either the first 2 and we add it with the third one, or we take the second 2, we add it with the first one. So this one is using axiom number 3. Then 0 multiplied by U plus minus 0 multiplied by U, this will give us 0. So this is using axiom number 5. If you have a vector with its negative vector, the result will be 0. Similarly for this one, 0 multiplied by U plus minus 0 multiplied by U, which is equal to 0. So this is axiom number 5. Now 0 is equal 0 multiplied by U plus 0. If you add 0 with any vector, this U will give us the vector. So that's mean using axiom number 4. So this one here it is by using 4. In 29, prove that minus 1 multiplied by u is equal minus u. Hence show that u plus minus 1 multiplied by u is equal to 0. Use some axiom and the result of exercise 27 and 26. So now we consider the given one, which is u plus minus 1 multiplied by u. So now using axiom 10, 1 multiplied by u will be u. So minus 1 multiplied by u should be equal minus u. So by axiom 10, u plus minus 1 multiplied by u, this one is just, let us write it here, it is just u is 1 multiplied by u plus this one also minus 1 multiplied by u. So now if we use axiom 8, c plus d multiplied by u is equal to cu plus du. So similarly, this one by axiom 8, one multiplied by u plus minus 1 multiplied by u, this is just is equal 1 plus minus 1 multiplied by u. So now 1 plus minus 1, it is 0 multiplied by u. So now by exercise 27, we say that 0 multiplied by u, it is just equal to 0. So by exercise 27, 0 multiplied by u, it is equal to 0. So thus we have u plus minus 1 multiplied by u, this is equal to 0. And by exercise 26, minus 1 multiplied by u, this is equal minus u, or we can use axiom number 10. So we prove here that we use first u plus minus 1 multiplied by u, this one is equal to 0. We use axiom 10 and axiom 8. Then we use exercise 26 to show that minus 1 multiplied by u, it is equal to minus the negative u.